Dear friends, Maths Aspirants Groups organizes online problem solving sessions to help the students who prepare for different competitive examinations like JAM, NET, GATE, etc. As a part of that series, today we have Dr. Mahesh TV is with us to engage a session on functions of several variables. Dr. Mahesh took his Ph.D. from Indian Institute of Space Science and Technology, Trivandrum, and his broad research area is Riemannian geometry. Mahesh did his M.Sc from Pondicherry University and M.Phil from Cochin University of Science and Technology. I'm very happy to introduce Dr. Mahesh to all our participants, and I hope that today's session will be really helpful because there may be many problems from the area of functions of several variables for the exams like JAM as well as NET. So I welcome everyone to this program. I use this opportunity to express my sincere gratitude and thanks to Dr. Mahesh for joining with us. Welcome, Mahesh.
Again, once again, and thank you for calling me. So this is, I think this is the third time I'm coming here. So very happy to be a part of this program. So we will look at some functions of several variable. Mostly I will discuss function of 2 variable and 3 variable. Okay. So today we will discuss multivariable calculus, or mostly function of 2 variable and 3 variable. So I focused only on the topics which is important for both the JAM and CSIR. So I prefer to this is the references I use. This calculus of my by work and a course in multivariable calculus by and analysis by Cropper and Demai. These are the 2 references I suggest. If you are interested more on this topic, you can look at these books.
So let us discuss this functions of 2 variable. So a function of 2 variable is simply a function f from D subset of R2 to R. So the domain is a subset of R2. Such functions are called a function of 2 variable. 2 independent variable are the usually we denoted by x and y. Okay. So these are some examples of function of 2 variable. So let us look at one. These are some examples. F of xy is equal to x plus y. F of xy is equal to x square plus y square. So these are some examples of function of 2 variables. So now we will I will give you a brief idea about the graph of these functions. So it's not easy to plot all the graph of functions. So graph of f from R2 to R is some function I have plotted here. This is f of xy is equal to x square plus y square. So this is the graph of f of xy is equal to x square plus y square. So we here the things we have to plot in 3D. So because there are 2 independent variable and 1 dependent variable, usually we denote it by z. So this is the graph of x square plus y square. This is a generalization of y is equal to x square. So this is called a paraboloid. Okay. So let me come to so 1 second. So most of the time plotting graph of such functions are difficult. So we will look at the some other way to understand the structure of the given function. So that is given by the level curve. Okay, level curve means that this is the definition of level curve. Let me just define it. So level curve is suppose you have a function f from D to R, and level curve corresponds to any C belongs to R is defined by this way. All those points whose image is f of xy is equal to C. So such of all xy belongs to R2 such that f of xy is equal to C is called the level curve of that given function. Okay. So in order to understand the geometry of the given function, we will use the level curve. So this is the example I have mentioned here. Once again, so the previous example itself. So how do we look at the level curve? So you look at the function f of xy is equal to x square plus y square. The level curve of f corresponds to C is set of all xy belong such that f of xy is equal to C. Here the function is x square plus y square. So you can just look at all those points x comma y such that x square plus y square is equal to root c square. In fact, it is in fact c I can write it as root c square. So it is in fact giving the circle. Okay. So once you look at the level curve, what you will get is a circle corresponds to the each c. So I have plotted some of them are here. So when c is equal to 1, you will get a unit circle. If c is equal to 2, you will get a circle of radius root 2. Then if c is equal to 3, you will get a circle of radius root 3. These are the examples of as a particular case of these c's. C is equal to 1, 2, and 3. So these are some example of level curve. So most of the times people used to in order to understand the geometry, people use these level curves. So I just want to mention these concepts. So let me come to the some more concepts which I am going to use regularly. That is the cylindrical and spherical coordinate. And I may just give you the brief idea about the cylindrical coordinate. So cylindrical coordinate is so you may use to represent the points in R3 in x, y, z. They are in fact the Cartesian coordinate or the rectangular coordinate. So instead of representing using these x, y, z coordinate system, we will represent the points as a point in the cylinder. So there three components are there. One is denoted by r, that is the radius of the cylinder, and theta is there, that is the angle with the x-axis, and z will be as it is, z. Okay. So the conversion formula I may just tell you. This is the conversion formula from cylinder to rectangular coordinate. Cartesian. So once you have a cylindrical coordinate r, theta, z, you can convert it into a rectangular by using this formula, right? X is equal to r cos theta, y is equal to r sin, z is equal. So these all are I think you guys are familiar with these things. You may have seen this thing in vector calculus. Most of the times you may have used this thing using the triple integral or double integral concepts. So these are the conversion formula. X equal to r cos theta, y is equal to r sin theta, and z is equal to z. And this is the reverse process. So once you have a rectangular coordinate, how do you go to the cylindrical coordinate? So to go to cylindrical coordinate, you have to take these conversions. R equal to root x square plus y square. Theta is sine inverse y by r for y positive, and cos inverse x by r for y negative, and z is as z is such. So this is the conversion formula from rectangle to cylindrical and cylindrical to rectangular coordinate. Similarly, you can talk the spherical coordinate also. I am not including those things here. So if it is required somewhere, then I will explain. Okay. Just recall the things. Okay. So let us come to the concept of limit and continuity in function of two variable. So most of the things you can think as a metric space. So metric space with the concepts in metric space we can always discuss here, because R2 is a metric space with the metric is there. Metric is the usual Euclidean distance. Okay, Euclidean metric. So all the things what I am discussing here in that setup, I will discuss this as I will consider this as a metric space with the metric as the Euclidean space. So then we can talk the continuity of the function using sequences in metric spaces. So all those things I may bring here. So you just look at how do we understand the concepts. So let us first define the sequence in R2. Okay, everything I am going to discuss in terms of sequences. So continuity we can discuss with respect to sequence. Suppose you have a function. I may just recall the things what you know in real analysis or single variable case. Suppose you have a function f from R to R. So how do you say this f is continuous at some point? How do we check using the sequences? So what let x0 is a point in R, then how you can check whether the function is continuous at x0 using the sequence definition. So how do we discuss that? So here thing is, if you take any sequences which converges to x0, you should show that f of x and also converges to f of x. right? So that is the definition of the continuity at x0 in terms of sequence. So if xn converges to x0, then f of xn should converges to f of x0. So if you are able to do these things, we can say f is continuous at x0. So for any sequence xn converges to x0, then f of xn also should converges to f of x0. That is the definition of continuity using the sequences. So the same idea I am going to generalize here. So let us look at the definition of sequence in R2. Okay. So a sequence in R2 is simply a function from natural number to R2. So usually we denote it by this way. So this is one notation, this one, or this is another notation for sequence. Sequence usually we denote by x and yn or u and vn. So as in the same sense, we say it is bounded if the norm of x and yn less than some alpha. If it is less than some fixed constant number alpha, the sequence is bounded. But you should be very careful. But here the modulus of x and yn is nothing but square root of xn square plus yn square, right? So you have to be very careful that the modulus of sequence x and yn less than or equal to alpha means root of xn square plus yn square less than alpha. It's not the usual metric in R. It's a usual metric in R2, in fact. So let me come to the definition. So let us look at when you say what do you mean by the convergence in R2. So you have a sequence xn and yn is said to be convergent in R2 if there exists some point x0 y0. So suppose there exists some point x0 y0 in R2 such that the usual epsilon n definition. For all epsilon greater than 0, you can find some stage. After that stage, all the points from the sequence x and yn should be in the ball with the center x0 y0 and radius epsilon. So always you can find some stage for the given epsilon positive. For a given epsilon positive, we can find some stage. After that stage, all the points in the sequence should lie in the ball with the center x0 y0 and radius epsilon. This ball is given here. So this all the ball is given by this equation. Ball is nothing but all those points x comma y belongs to R2 such that the root of x minus x0 square plus y minus y0 square less than epsilon. So you can just look at the figure. So if you want, I can just draw it here. It is simply you can understand the concepts using the figure. So for somewhere here x0 y0 is there, and you have a ball with a radius epsilon. So what exactly this is? After a stage, all the points in the sequence. So first points can be somewhere here, doesn't matter. Second point also somewhere here. So it comes like this. After a stage, all the points should be inside of this. That is the meaning. So the sequence x and yn is converging to x0 y0 means for given epsilon, you can find some stage. After that stage, all the points in the sequence should lie in that board. Okay. So let me. So usually we write it as x and yn converges to x0 y0. So you can easily observe that once x and yn converges to x0 y0, this xn should converges to x0 and yn should converges to y0. The component-wise convergence is also there. Okay. So now let us look at the definition of continuity using sequence. So you have a function f from D to R and x0 y0 is a point in D. So f is from D to R and x0 y0 is a point in D. So we say it is f is continuous at the point x0 y0. If for every sequence, so whatever the sequence you take from here, such that x and yn converges to x0 y0, we have f of x and yn converges to f of x0. So for all the sequence x and yn which converges to x0 y0, f of x and yn should converges to f of x0 y0. So in that case, we say f is continuous at x0 y0. And so we say f is continuous on a domain if it is continuous at every point on the domain. So let me look at the let me look at some examples for continuous functions. So we will see So this is the first example, constant function. So this one is a constant function. F of xy is equal to c. F of from some d subset of R2 to R, f of xy is equal to c for all xy belongs to D. You can easily observe that this function is continuous, right? So, if you want to check using the definition, you take any sequence. So you take some sequence x and y, and arbitrarily one sequence x and y is taken. You assume that this converges to some, this is in some point x0, y0. x0, y0 is an arbitrary point. So you look at this, f of xn is converging to x and yn is converging to x0, y0. Now you can consider f of x and yn, right? F of x and yn is in fact c only. So always it is c. So it should converge to c only. So what is the c? C is f of x0, y. So if you take any sequence x and yn which converges to the point x0, y0, f of x and yn also converges to f of x0, y0. That means f is continuous at x0, y0. This you can do for any x0, y0 in the domain. So whatever the x0, y0 you are taking, the same thing I can do. So f is continuous on all the points on the domain. So constant functions are always continuous. So now let us look at another example. So this function, let me look at this example. F from R2 to R given by f of xy is equal to root of x square plus y square. So let us prove this. This is continuous on the entire domain. Okay. So in order to check this is continuous on the entire domain, I need to show that this is continuous at some point x0, y0. So let x0, y0 is an arbitrary point from the domain. So I wanted to check that whether the function is continuous at x0, y0. So consider a sequence. Consider the sequence x and yn converges to x0, y0. Okay. Now you can look at f of x and yn. So what is f of x and yn? So since x and yn converges to x0, y0, so this implies xn is converging to x0 and yn is converging to y0. Each component will converge to the corresponding. The xn should converge to x0 and yn should converge to y0. Now you look at f of x and yn. So what happens? What is f of x and yn? So f of x and yn should be is equal to root of xn square plus yn square. Since xn converges to x0, we can write one more things here. Xn square will converge to x0 square and yn square should converge to y0 square. So we can club all the things here. So this implies root of this will converge to root of x0 square plus y0 square. So I have used a lot of things here. Continuity of the root function I have used, and the sum of two convergent sequences again convergent, and this converges to the sum of the limit. That also I have used. So you can this also implies if you want, you can write one more step here. Xn square plus yn square, that should converge to x0 square plus y0 square. Okay, so root of xn square plus yn square converges to root of x0 square plus y0 square because of the continuity of the root function. Root function is a continuous function from set of positive real number to R. So this is a continuous function. So xn square plus yn square converges to x0 square plus y0 square. That implies root of xn square plus yn square should converge to root of x0 square plus y0 square. So this implies this function is a continuous function. Root of x square plus y square is a continuous function. This is continuous at x0, y0. Since it is an arbitrary point, is continuous on the entire domain. Okay. So let us give another example. So let us look at this example. F from R2 to R2 defined by as the following. So for whenever xy not equal to 0, the function is xy divided by xy plus y square. For xy is equal to 0, it is 0. So now I wanted to look at whether this function is continuous at 0, 0. Okay. So I will show that this function is not continuous at 0, 0. So f is not continuous at 0, 0. So to show that, I'm considering a sequence. Consider. So in order to show it is not continuous, it is enough to produce one sequence which converges to 0, 0, but f of x and yn does not converge to f of 0, 0. So that is enough, right? So let us consider the sequence. Consider x and yn. That is equal to 1 by n, 1 by n. So this is the sequence. So 1 by n both is going to 0. So you can easily observe that this converges to 0, 0. So now you consider this f of x and y. So now what is f of x and y? This is in fact xn yn divided by xn square plus yn square, right? That is our function. F of x, y is f of x, y is exactly xy divided by x square plus y square, right? So this is the case. Here xn is 1 by n and yn is also 1 by n. So what you will get is this is equal to 1 by n square in the numerator. Denominator you will get 2 by n square. 1 by n square plus 1 by n square, that is 2 by n square. So n square will cancel. So it will be 1 by 2. But what is f of 0, 0? But f of 0, 0 is 0, right? So f of x and yn does not converge to so f of x and yn does not converge to f of 0, 0. That means f is not continuous at 0, 0. So to show this is not continuous, it is enough to produce one sequence which converges to 0, 0 and show that f of x and yn is not converging to f of 0, 0. So we can conclude that f is not continuous at 0, 0. So for this sequence 1 by n, which is converging to 0, 0, and its image f of x and yn, that is in fact you are getting 1 by 2, that is going to 1 by 2 only, that is not equal to f of 0, 0. So the sequence is so the function is not continuous at 0, 0. So now I will give you one more example to show that whether the function is continuous or not. So I can show this function is continuous at 0, 0. I will show this function is continuous at 0, 0. So is continuous at 0, 0. So let us look at why it is continuous at 0, 0. To show that, let me so in order to show something is continuous at some point, you have to consider an arbitrary sequence. So x and yn is an arbitrary sequence. You show that x and yn is you have to take as a sequence x and yn which converges to 0, 0. Then you show that f of x and yn should converge to f of 0, 0. Okay. So let us take an arbitrary sequence x and yn. So let x and yn be an arbitrary sequence. Sequence with the x and yn converges to 0, 0. Okay, so this is an arbitrary sequence with the x and yn converges to 0, 0. Now you look at f of x and yn. So what you will get f of x and yn? F of x and yn is in fact xn square. You just substitute there. So x square y divided by x square plus y square is your function. So you will get xn square yn divided by xn square plus yn square. Okay. So now you can observe that this, what is the relation between this xn square and xn square plus yn square? So this one will be bigger, right? Xn square is always less than or equal to xn square plus yn square. So what you can say is this implies this xn square by xn square plus yn square is always less than or equal to 1, right? So using that, you can see that this modulus of f of x and yn, you can say this is always less than or equal to mod yn, because this xn square divided by xn square plus yn square is always less than or equal to 1. So this quantity is less than or equal to 1. So this is always less than or equal to yn. So now you see your xn and yn are going to 0, 0. So yn is also going to 0. So you apply the limit on both sides. So what you will get? So this implies limit x and yn tends to 0, 0 f of x and yn. So this is in fact, or you can, or if you want, I can write in a different way. So from here, what you can say is, you can directly write it from here, right? No need to make confusion. So here you see your x and yn is going to 0, 0, right? So x and yn is going to 0, 0. Here you have x and yn is going to 0, 0. So yn is also going to 0. So it says this quantity will go to 0, and this is always a positive number. So using this Q's theorem, what you can say, the in between things should go to 0. So that is limit n tending to infinity f of x and yn. This is equal to 0. That is exactly your f of 0, 0. So if x and yn converges to 0, 0, then f of x and yn is going to f of 0, 0. That means f is continuous at 0, 0. So this function is continuous at 0, 0. So here we have taken arbitrary sequences, so we can conclude that f is continuous at 0, 0. So this function is continuous at 0, 0. The previous one is not continuous at 0, 0. So you have to be very careful. So in order to show something is not continuous, you need to produce at least one sequence which going to the corresponding point, and its image is not going to the image of the point. Okay. But to show something is continuous, you have to start with some arbitrary sequences and show that the f of x and yn also will converge to the f of x naught y naught if x and yn is going to x naught y naught. Okay, so that is the idea. So that is the way you have to check whether the given function is continuous or not. So I will give you two exercises. You can try it later. So this function, you can just try whether this function is continuous or not. So it is asks you to show that this function is not continuous at 0, 0. So you have to produce some sequences. So this is 4, right? Here it is 4. X square y divided by x raised to 4 plus y square. Okay, 1 second. So this one is x square y divided by x raised to 4 plus y square. Okay, so you can show that this function is not continuous at 0, 0. So you should produce at least one sequence. Their image is going to 0. So x and yn should go to 0, 0. But f of x and yn does not go to f of 0, 0. You can just construct one sequences and show that this is not continuous at 0, 0. Similarly, I'm asking you one more question. You can show that this function is continuous at 0, 0. So here the difference is, here numerator you have x square y. Here it is x cube y divided by x raised to 4 plus y square. Okay. So the numerator you have x cube y here. For the previous one, it is x square y. So the first one is not continuous at 0, 0, but the second one is continuous at 0, 0. You can show that. So show this one is continuous at 0, 0. So the only difference is here it is x cube, the previous one is x square. So these are two exercises. You just try this, okay? So let me come to this one remark. You can just, as in the case of real analysis, you can so single variable case, you can observe that the composition of continuous function are also continuous. So in the appropriate domains, okay. So once you have to take the composition, the domain should be very clear, well understood. Then only you can talk about the composition. So then, if these two functions are continuous, then you can talk that f composite G also continuous. So using that, you can check some of the following things are continuous. Okay, there are some more examples. You just look at the sin xy. You can say this function is continuous. So I may prove that this function is continuous using the previous observation remark. So you know the sine function is continuous from R to R, and this xy in fact giving you a polynomial. So you can think this as a composition of two continuous functions. So that is the idea. So let us define it as a composition of two functions. So define small f from R to R as by f of x is equal to sin x. We know this function is continuous, and you take some g from R2 to R. This is g of x comma y is equal to xy. So you can think this function is, you can show that this function is also continuous because it is a product of two polynomials. In fact, so x and yn go into x naught, y naught will give xn will go into x naught, yn is also going to x naught, then xn into yn will go into x naught, y naught. So you can easily show this is continuous. So just I may write it here. So x and yn, you can say x and yn is going to x naught, y naught. Then this implies xn will go into x naught, yn will converge to y naught. So it implies x and yn will go into x naught, y naught. So this is your f of x and g of x and yn. So this is your g of x and yn, and this is your g of x naught, y naught. So this function is a continuous function. G of xy is equal to xy is a continuous function. So f is a continuous function, f is sine function, and g is given by this one, g of xy is equal to xy, that is also continuous function. So you can take the composition of these two. So you can easily observe that this capital F of xy is nothing but capital F of xy is nothing but f composite g of xy. So what is it? This is your f of g of xy. So this is in fact sine of xy. So this function is a continuous function. The composition of two continuous function is continuous implies capital F is continuous. Similarly, you can look at this function also. You can just try this one. Here you have x plus y. So again, instead of xy, you have x plus y. So x and y are polynomial. So it should be continuous function. Inside thing it should be continuous. This should be continuous. And cos is also continuous function. The composition you will give cos of x plus y. So that is a continuous function. You can just verify this. Okay, the similar way. So now let us look at the definition of uniform continuity. So uniform continuity you might have learned in single variable case, function of real variable, single variable. The you might have seen the definition of using the sequences. So what was it? So when you have two sequences, so you have to consider two sequences for any sequences x and yn and u and vn. This such that the norm of x and yn minus norm of u and vn go into 0 should imply modulus of f of x and minus f of x and yn minus f of u and vn should goes to 0. So I may state the single variable case first, then we will come back here. So you have a function f from some e subset of R to R. So when you say f is uniformly continuous, so uniform continuity is in fact a property of a domain. So so we can say, so if for any sequence, if for any sequences xn and yn with the modulus xn minus yn modulus xn minus yn going to 0 implies modulus f of xn minus f of yn converges. So if it is happening, then we can say f is uniformly continuous on, then f is uniformly continuous on E. Okay, so E is a subset of R. Then for any sequences xn and yn with the modulus of xn minus yn going to 0 should implies modulus of f of xn minus f of yn should goes to 0. Then we can conclude that f is uniformly continuous on the domain E. So the same thing I am extending for the function of two variable. So you see here, you have a domain D subset of R2 and a function f from D to R is said to be uniformly continuous on D. So f is said to be uniformly continuous on D if for any sequences xn, yn and un, vn in D such that the norm of xn, yn converges to 0, we have these conditions: f of xn, yn minus f of un, vn, the modulus of that should goes to 0. So if you can prove this thing, then we can conclude f is uniformly continuous on the given domain for any sequences xn, yn and un, vn such that the norm should goes to 0. This we should get this part, modulus of f of xn, yn minus f of un, vn should goes to 0. Then we can conclude that f is uniformly continuous on D. So this is in fact same the epsilon delta definition, but I am not going into that way. You just, so this will be very useful for computing the or this will be very useful for checking whether the given function is uniformly continuous or not. Okay, instead of going to this epsilon delta definition. So I may look at some examples in R2. So let us look at some examples. So one more thing I wanted to discuss. So any continuous function on the closed and bounded subset should be uniformly continuous, right? Because we have the result that any continuous function on a compact set is uniformly continuous. So if is continuous, it's defined on some compact subset, then it has to be continuous, uniformly continuous, right? So here D is closed and bounded subset of R2. So every closed and bounded subset is compact. So continuous function defined on D has to be uniformly continuous. That is one proposition. Okay, now let us look at the example. Okay, this example is the first one, f from R2 to R defined by f of x y is equal to x plus y. Now you can easily observe that this function is uniformly continuous. Why? So you consider two sequences. So let x and yn and un, vn are two sequences. Sequences with the modulus of or norm of x and yn minus un, vn converges to 0. Here the norm means exactly the Euclidean distance on R2. Okay, so this you can compute. This will give you so that is the square root of xn minus un square plus yn minus vn square is going to 0. That is the thing you have. Now you look at this one, f of xn. Consider modulus of f of xn yn minus f of un, vn. So what you will get? What is f of xn yn? That is xn plus yn, right? So x plus y is your function. So f of xn yn means xn plus yn. So you can just replace this by xn plus yn. So this is xn plus yn, and un plus vn is, you have minus un plus vn. So you can just combine this thing So what you will get modulus of xn minus un. So you can, I may write it, this is less than or equal to modulus of xn minus un plus modulus of yn minus vn. So again, each component you can make, this is less than, each one is less than the square root, right? So this is less than or equal to 2 times square root of mod xn minus un square plus yn minus vn square. So this one is less than the square root, and this is also less than the square root. So each term is less than the square. So you will get 2 times square root. So what exactly we are having? We are having the sequences xn, yn, and un, vn with the square root is going to 0, right? So this one is going to 0. So left side, this is going to 0 as n tends to infinity. So this value is also should goes to 0 because this is a modulus value. This is always positive. So right side and left side is right side is going to 0 and left side is you have a 0. So in between value should be 0, right? In between value should goes to 0. So that is limit n tends to infinity modulus f of xn yn minus f of un vn should be 0. So that means f is uniformly continuous on R2, right? So it is defined on the area domain R2. So you can easily observe this function is uniformly continuous. So now I will give you one example which is not a uniformly continuous. This is just a generalization of the example 1 by x. So you may recall that 1 by x is not a uniformly continuous on. So recall 1 by x is not a uniformly continuous, only continuous on open 0 close to 1. Okay, if you want close to 1 you can write, or this is not uniformly continuous because when you go to very close to 0 you have a trouble, right? So once you use the epsilon delta thing you can observe that. So you cannot choose delta purely depending on epsilons. It depends on the points also. Okay. So now you see this example, this is in fact the generalization of that example. So it is somewhat analog of that example. So you have a domain D subset of R2 and f from D to R. So D is given by this equation. So this is the D. This is a set of all xy belongs to R2, such that xy belongs to closed interval 0, 1. And I am not including the point 0, 0. So what is the domain D? I may draw it here. This is the cross product of closed interval 0, 1. So you have 0 is there, 1 is here, and 1 is here. So once you look at this cross product, you will get this rectangle, right? But this point is not included. I remove this point. Only one. This point is removed. 0, 0 is not there. All other points are there. So including these inside points, I'm taking. So, but this point is not there. Okay, this is the domain D. Okay. Now I define the function f of xy as 1 by x plus y. That is my function. So now I wanted to check whether this function is uniformly continuous on this domain. Okay. So by our definition, to check something is uniformly continuous, you have to look at the sequences. So two sequences you have, their difference should go to 0, but the image value should not go to the difference of the image should not go to 0. So here I am showing that this function is not uniformly continuous. So let us look at the how we will do it. Okay. So let me yeah. So we will see how we will obtain it. So we have to consider two sequences. So let me give you two sequences. Let I will show this function is not uniformly continuous. Let x and y n. So I will consider this x and y n as 1 by n 0. So this is one sequence, and the second one is u n v n is equal to 1 by n plus 1 0. So what we have to do is we should construct at least two sequences So their difference should goes to 0, but difference of the image should not goes to 0. If you are able to consider such a sequences, we can conclude that this function is not uniformly continuous because it contradicts our definition, right? So let me look at the difference of these two sequences. First, I have to check whether the difference is going to 0 or the norm of the difference. Okay, so let me look at the norm of x and yn minus u and vn. Okay, so what was it? This is in fact a norm of 1 by n minus 1 by n plus 1 comma 0, right? So you have to look at the norm of this one. So this is you first simplify this 1 by n minus 1 by n plus 1. So this is in fact norm of 1 by n into n plus 1, right? Because if you cross multiply this, n will cancel. So 1 by n into n plus 1 will come. So this is in fact the norm of this 1 by n into n plus 1 comma 0. So this is nothing but 1 by n into n plus 1. So you can just verify this. You just take the square root of first term square plus second term, and then square root and square will cancel. So you will get 1 by n into n plus 1. This is just a distance in R2, right? Euclidean distance only. So it is 1 by n into n plus 1, which will goes to 0 as n tends to infinity. As n tends to infinity. So the difference is going to, norm of the difference is going to 0 as n tends to infinity. Now you look at what happened to this modulus of f of x and y n minus f of u and vn. So you just consider this. So what is your f of xy? F of xy is 1 by x plus y. So you give the values there. So what you will get? This is modulus f of 1 by n comma 0 minus f of 1 by n plus 1 comma 0. So what you will get? This value is 1 by this is in fact 1 by x plus y is there. So 1 by n plus 0. So that is 1 by n. So that is n, right? Minus this is 1 by n plus 1. So that will be n plus 1. So the difference is always 1. The modulus value is always 1, which is not going to 0. So the norm of x and yn minus u and vn is going to 0 as n tends to infinity. But the modulus of f of x and yn minus f of u and vn is not going to 0 as n tends to infinity. That by the definition of a uniform continuity, we can conclude that f is not uniformly continuous. So f is not uniformly continuous. The conclusion is f is not uniformly continuous. So this is the thing. Now again, you can check one more example is there. You just verify this. I have given the hint here. So this is also generalization of the example f of x is equal to x square. You can recall that f of x is equal to x square is not uniformly continuous from R to R. The same way you can observe this f of xy is equal to x square plus y square is also not uniformly continuous. You can take these two sequences. So these are the sequences you have to consider. This one and this one. You can just verify this, okay? So this is your duty. You just verify this. Verify. So you can easily verify this whether this x and y the difference should goes to 0 or the what happened to the image of the f of x and minus what happened to the difference of the images. So you can observe that the image will not go to 0. So we can conclude this is also not uniformly continuous. Okay. So let me just now I wanted to recall the basics of the limit of how do you compute exactly the limit of a function at a point. Okay. So let's just recall limit at x0 or for the given function. So we know that how do we look at the limit? So what exactly the limit x tending to x0 f of x means? So what do you mean by these quantities? So you have to consider the real line and you have a point x0. So you can approach this point in a two different way from the right and left. So you will get a left hand limit and right hand limit. Both has to be equal. Then we say the limit exists, right? That equal value is denoted by the limit x tends to x0 f of x. So that is the definition. So in a similar fashion, we can look at the limit in R2. So suppose you take a function, let f is from R2 to R. So you have a function. Now you take a point, and x0, y0 is a point in R2. So how do I check the limit exists or not? So in order to check whether the limit exists or not, you have to consider some points. So the x0, y0 is there. So you want to look at whether the limit exists at x0, y0. So what you have to do is you have to look at all the possible path passing through this, all the possible curve along this point. So that is, in fact, there are infinitely many curves. So along each curve, you approach the point x0, y0. You should approach along each curve x0, y0. All the cases, if you look at the corresponding changes in f, if it is equal in all curves, then we can say the limit at x0, y0 exists. As in the previous cases, your point is in R to R. There are only two possibilities. You can approach from the right or left. But now the point is in R2, so you have infinitely many ways to approach that point. So that actually given by the infinitely many curves passing through the x0, y0. Along each curve, you can approach the point x0, y0. So in each curve, you should look at the corresponding changes in f. So let me say, suppose you take some curve C1, so you call it as C1. Then you look at limit xy tending to x0, y0 along C1 f of xy. Suppose this value is some L1. Again, you can look at the limit along some other L2. So it can be some other L2. So if all those values are equal, if all those such values are equal, we say the limit at x0, y0 exists. Okay. So in order to check something, whether the limit exists or not, we have to consider all the path passing through that point. Along each path, you should get the same limit. Then only you can say the limit at x0, y0, same value. Then only you can say the limit at x0, y0 should exist. So let me look at the some examples, so that we have already discussed. We have already checked whether continuity of such functions, but now we will see how we will check whether the limit value exists or not. So for this example, you can say the limit at x0, y0 does not exist. So we can say the limit xy tending to 0, 0 f of xy does not exist. Does not exist. So let me see how do we check it. Okay. So to see this, you have to consider the line which passes through 0. So you have a point 0, 0. You should consider all the line passing through the 0, 0, all the curve passing through the 0, 0. I may take a family of curve y is equal to mx. So you can just take y is equal to mx. That gives a family of curves, family of lines which passes through the origin. So m is the slope of the corresponding lines. So once you approach these 0, 0 along this curve line, what happens? What you will get f of x comma mx. So that value is x into mx divided by x square plus m square x square. So you can just simplify this. So this will be m divided by 1 plus m square, right? M divided by 1 plus m square. So the limit xy tending to 0, 0 f of xy along y equal to mx. I'm looking along y equal to mx. That will be simply m divided by 1 plus m square. So that value is depending upon the slope. So if slope is equal to 1, you will get a 1 by 2. If slope is equal to 2, you will get a 2 by 5, etc. So it depends upon the slope. So each curve, each line, you will get a different value. So the limit at x 0, 0 does not exist. So it depends on the slope, the value of m. M. So it depends on the value of m. So we can conclude that the limit does not exist. So that is limit xy tending to 0, 0 f of xy does not exist. Okay. So this is the thing. Now we will see one more example. So So you can just look at this example. So I will show that this limit exists at 0, 0. So what actually I wanted to do is I wanted to look at whether the limit at 0, 0 exists. Okay. So the question is limit xy tending to 0, 0 f of xy exist. So let's just look at this. So what you are having is you look at this limit x sine 1 by y. So what is your function? F of xy is equal to x sine 1 by y. So now you can just take the modulus on both sides. So modulus of this one will be this one. But you know that sine value is bounded by 1 and minus 1 term. So this is always less than or equal to mod x. So once your xy is going to 0, 0, your x should goes to 0, right? So you can apply limit on both sides. So what happens? So this value will goes to 0. As xy is going to 0, 0, as xy is going to 0, 0, x should goes to 0. So mod x should goes to 0. So but here you have always greater than or equal to 0. So the in between value should goes to 0. So this implies limit xy tending to 0, 0, f of xy is exactly equal to 0. That is your f of 0, 0. So the limit exists, and you can in fact check this is a continuous function because that is your f of 0, 0, right? When y is 0, you will get a 0 only. That is your value. So f of 0, 0 is 0 here. Okay. So in fact, the limit exists. That value is 0 here. So only need to bound the sine function. That's all. Okay. Now I will discuss some concepts called partial derivatives. So next I will discuss partial derivative. Then we will go to the definition of derivatives of the function, multivariable case. Then we will look at this function of this directional derivative and the relation between total derivative and directional derivative. So then we will go to some problems, okay? Previous year problems. Let me quickly recall what you mean by the partial derivatives. So we have a function f and its domain is D. So D is here. So f is function from D to R. So any function and x0, y0 is some point in D. So let me define two sets D1 and D2. D1 is given by this way. So I look at all those points. X belongs to us, so that x comma y0 belongs to D. So this is in fact, so if you look at as a point in R2, you have a point x0, y0 here. So what I am considering is, I look at all those points x such that x, y0 belongs to D. Okay. So somewhere here you have, once again, so somewhere here you have D. So this is your D. So you look at this line, okay. This is the line x0 y, right? This is the line x0 y. So all the points are always x coordinate is always x0. And if you have another line, this one is your line with this one is D2, right? The D1, right? So here you have y coordinate is fixed. Y is always y0. Now what exactly you are looking is D1 is all those points such that x, y0 belongs to D. So you have to take this much portion. That is your D1. And D2 is you have to take this much portion. That is your D2, this one. This is your D2 and this red line. So those things which is inside D, that is your D1. Okay. Now you can define partial derivative as follows. See, if x0 is a interior point of D1. So suppose x0 is interior point of the D1, then we define the partial derivative with respect to x at x0, y0 as this one, right? Limit h tends to 0. So this is the definition of the partial derivative. So limit h tends to 0, f of x0 plus h comma y0 minus f of x0 y0 divided by h. So this is the partial derivative. at x0 y0. Okay, and similarly, that is we denoted by this way. So this is the way we denote the partial derivative. So we are making only the increment in the first variable, f of x0 plus h, comma y0 minus f of x0 y0 divided by h. The similar way we can define the partial derivative of y, partial derivative with respect to y at x0 y0. So this here you have to make the increments only in the second variable y0 plus h. So this is the thing. This is the one you have the partial derivatives. Okay. Fy at, so these quantities are denoted by fx at x0 y0 and fy at x0 y0. So let me introduce one more notation. So this one, dou f by dou x at x0 y0 and dou f by dou y at x0. This is another notation for the partial derivatives. Okay, another notation. Now I will give you the definition of the total derivative for the function of two variables. So you just so I'm not going to introduce these general definition from Rn to Rm. So that is in fact not needed for us. So we only need to look at the function from R2 to R. So their case also you can see how you will define the definition of define this total derivative. Okay. So the definition of total derivative. Just of f from the subset of R2 to R. So let me look at how do you define total derivative at a point. Okay. So so usually this is in fact a total derivative you can view as a linear map. So in order to discuss all those things, we need a more idea about this Fisher derivative. I'm not going into that much detail. So you can see so the total derivative of f from D subset of R2 to R is at x0 y0. So let x0 y0 is a point in D. So the total derivative will be denoted by usually df at x0 y0. So you can just observe this is in fact this value should be in fact fx at x0 y0. So I may, so you can think as this as a vector fx at x0 y0 and fy at x0 y0 such that limit h1 comma h2 tends to 0 0 modulus of f of x0 plus h1 y0 plus h2 minus f of x0 y0 minus df at x0 y0 into h1 dot product you have to take. Sorry. Minus df x0 y0 dot product h1 comma h2 modulus divided by root of h1 square plus h2 square. It should be 0. Okay. So what exactly I'm saying? So this quantity is called the total derivative of f at x0 y0. This is the total derivative. Total derivative of f at x0 y0, provided this limit should be 0. Okay. So this limit should be 0. So f of x0 plus h1 y0 plus h2 minus f of x0 y0 minus df df at x naught y naught dot h1 comma h2. So you should take the this is in fact your del f, right? Del f at x naught y naught. The gradient of f at x naught y naught. That is in fact the derivative of the function. If the derivative exists, it should be the del f, and it is given by this equation. So this quantity should 0. So then only we can say this will be the derivative. So the derivative is the quantity which satisfies these equations. Okay. So that is in fact given by the equation. Once it is differentiable, once the function is once the total derivative exists at some point x naught y naught, you can easily compute the total derivative. There is nothing but df at x naught y naught. That is your del f, fx at x naught y naught, comma fy at x naught y naught. This vector is your derivative at x naught y naught. Okay. So let me. So this is the idea. So this is the total derivative. So suppose you are asking you to find whether the function is differentiable at some point. So only thing you need to compute partial derivative at x naught y naught and partial derivative with respect to y at x naught y naught. Then what you have to do is you look at this df of x naught y naught and check whether this quantity is going to 0. So if it is going to 0, you can conclude that f is differentiable at that given point. So if it is not going to 0, you can conclude that the function is not differentiable at the given point. Okay, the only thing you have to verify this thing, whether this ratio is going to 0. Okay. So now one more thing I wanted to discuss, this directional derivative. So let me look at the definition of directional derivative. So let f is from some d subset of R2 to R. You have a function, and x naught y naught is some point in D, and u is equal to some u1 plus iu2 is a unit vector. Okay, unit vector. So unit vector means this u1 square plus u2 square is exactly equal to 1. Now I will look at this the directional derivative of f at x naught y naught in the direction of u. Okay, the directional derivative of f at x naught y naught in the direction of u1 u, the direction of u, the direction of u at the x naught y naught. Oh, sorry, in the direction of u, right? Is the direction of u is limit is denoted by this way, du f at x naught y naught. This is equal to limit t tending to 0 f of x naught plus t u1 and y naught plus t u2 minus f of x naught y naught divided by t. So this is the directional derivative of f at the x naught y naught in the direction of the unit vector u1 plus iu2. Okay, so you have a f and x naught y naught is in the domain. You are trying to find the directional derivative. This is the way it is defined. So this is the definition. So du of f at x naught y naught is nothing but limit t tending to 0 f of x naught plus tu1 comma y naught plus tu2 minus f of x naught divided by t. So this is the directional derivative. So you might have seen the directional derivative and total derivative. So you might have seen the definition of in the smaller class that du of f at x naught y naught is equal to del f at x naught y naught dot u. So this thing you might have seen in your smaller class, but this is not in fact true for all functions. You cannot write it as in this is not a general result. So this is valid only for those functions whose total derivative exists. Okay. So I may write the statement. So yeah. So equality is, so in fact, so this equality is valid. So I may write it here. This is valid. This is valid only for differentiable functions. That means the total derivative should exist. So I have given a lot of some examples for in which they are not equal. That is there in my previous video. You can just look at it is there. So I'm not including those things here because of the shortage of time. So you can just look at that things. Okay. So du of f of x naught y naught is always not equal to del f of x naught y naught dot u. So this quantity is equal when f is differentiable. Okay. So these all are the some basic concepts I wanted to mention. I just wanted to discuss more problems on regarding this for the previous year questions. Mostly I will discuss the problems from JAM and CSIR net. So let us look at some problems with these concepts. So then it will be then you can clear more concepts. If you have any doubt, that time we can discuss. Okay. So let me look at some problems. We have a lot of problems regarding this. So I have arranged it here. So let us look at this. Okay. So this is the 2021 JAM problem. So this one you can easily compute. So you just see what is the domain here. You have a domain D is equal to R2 minus 0, 0. And you have the functions to U and V from D to R. So they are given by U of xy is equal to x square minus y square, and if U of xy is equal to x into y. Now, so the del U and del V are the gradient. So the question is whether del U and del V are parallel or del U and del V are perpendicular. So that are the questions. So first you compute del U and del V. So what you will get del U? You can just try. So you can first you compute this del U. So del U is the gradient, right? Dou U by dou x. So that will give you a vector dou U by dou x and dou U by dou y. So what is this value? You can just compute dou U by dou x is 2x and dou U by dou y is minus 2y. Again, del V is equal to, you can just compute that is dou V by dou x and dou V by dou y. So dou V by dou x and dou V by dou y. So what can you say about this? Dou V by dou x is y and dou V by dou y is x. So these are the things. Now you can look at this. So you can just check whether these are parallel or perpendicular. So you can just look at del V dot perpendicular means their dot product should be 0, right? Two vector is perpendicular means their dot product has to be 0. Parallel means both as in the one should be the multiple of the other, right? And yeah, that is the thing you have to check. So you just check whether this is the dot product is 0. So what happens? Del U dot del V, what you will get? The dot product is 2xy minus 2yx. So they are 0, right? For whatever x and y, it will be 0. So their dot product is 0 means they are perpendicular. So what is the answer? The first option is wrong, right? Del U and del V are parallel at each point is wrong. So this is wrong. First answer is wrong. What about the second one? Del U and del V are perpendicular at each point. So that is correct. They are perpendicular. Now what about the third one? Del U and del V does not exist at some point. That is also wrong because every point they are del U and del V are existing. Gradient is existing always. So because they are nice polynomials, there is no problem. So what about the last option? Del U and del V at each point of the spans R2. Tell me what about this thing? What you can say about this? The last option. Tell me. What about the last option? Whether that is correct or wrong? So what you got is del U and del V are perpendicular. So two vectors in R2 are perpendicular means what you
They
can
will
say?
span.
They spans the entire R2, right? Span of two perpendicular vector will give you entire R2.
D
Because
is
the
given as
dimension of
R2 minus 0, 0. So they are non-zero vectors already.
yeah, they are non-zeros. Fine. Yeah, they are non-zero vectors. So that is fine. They are orthogonal also. So their span will give you entire R2 because what is the dimension of R2 as a vector space? So these two vectors should be linearly independent, right? That is the geometrically it says the linearly independent means there should be perpendicular, right? So that exactly the idea. So these
Yes,
two are
sir.
yeah, two vectors are perpendicular means they are linearly independent, and the dimension of R2 over R is in fact 2. So two linearly independent vectors will automatically span entire R2. The linearly independent two vectors will span R2 because the dimension of R2 is 2. So this del U and del V will span R2. So this is also true. So this is a multi-options question. So both B and D are true. You understand this? Any doubt? Any doubt in this question?
No, sir.
Okay. So let us look at another question. So this is also last 2021 question. Yeah. So this one. So I already did this question, right? So yeah, anyway, you just look at here. So D is a subset of R2 where D is equal to R2 minus x comma 0. So what exactly you are D? You are removing the x-axis, right? You can just see here. This is your R2 and x-axis is there. So these points you are in fact removing. Okay. So all the points with the white coordinate is removed. So your D is the remaining portions. So that is your D. Now the function is f of xy is equal to x into sine 1 by y. So what can you say about this function? Whether this function is continuous on entire D? I'm talking only in D, not included this x-axis. So D is the remaining points. So what can you say about the continuity of function on D? Tell me whether this function is continuous or not. Tell me what is your answer? Whether it is continuous or not.
Yes, sir.
Continuous, right? Because x is a polynomial is fine, and you have 1 by y that is continuous apart from where y is not equal to 0. So those points already I removed. So 1 by y is continuous on the other portions, right? Then sine of 1 by y you can think as a composition that is also continuous. So this product of continuous functions that will give you a continuous function on the entire domain D. So you are not included the x-axis. The x-axis only have the trouble. So once y is 0, the sine 1 by y will come. That makes a problem. So those points I have not included. So all other points are there. So wherever the trouble that I have already removed. So this function is always continuous on the entire domain D. Clear? Is that clear?
Yes, sir.
Yes, sir.
Okay. So what about the second option? So the first option is wrong, right? F is discontinuous on D is wrong. Now you look at the second option. F is a continuous function on D and cannot be extended continuously to any point outside D. Is that correct? Okay, let it be there. Before going to that, you just look at the third option. F is continuous on D and can extended continuously to D union 0, 0. So the only thing you are including 0, 0 here. So second option we will look at later. So first you look at the third option. So you have a continuous function on D and can extend continuously on D union 0, 0. That is the third option. So only thing you need to look at whether the limit at 0, 0 exists. Okay. Suppose the limit at 0, 0 exists, you can say that it can extend continuously on D union 0, 0. So you check whether the limit at 0, 0 exists. So how do you check? So what should be the limit? So limit xy tending to 0, 0, f of xy you should find. What is it? Limit xy tending to 0, 0, x sine 1 by y. So you should check whether the limit at 0, 0 exists. Okay. So how do you check it? X into sine 1 by y.
We can
So
estimate this, like
yeah, this
sign is
this thing I
bounded.
have already done. Yeah, because its sign is bounded, so this limit should be 0, right? That thing I have already done. So you can just take the modulus. So what happens? So I will tell you why it is 0. So you take the modulus of x sine 1 by y. So it is less than or equal to mod x. So now as xy is going to 0, 0, so both end will go to 0. So here it is always greater than or equal to 0. As x tends to 0, it will go to 0. So using the estimate, you can say this in between thing also will goes to 0. So it has to goes to 0. So both end is going to 0. So the in between thing also has to goes to 0. So you can say limit xy tending to 0, 0, x sine 1 by y is 0. Okay. So the limit at 0, 0 is exists. So you can make it a continuous function on D union 0, 0. That is fine, right? So the same function you can extend continuously on D union 0, 0. So what do you know about the second option? The third option. Third option is correct. What about the second option now?
It's wrong.
Yeah, it is wrong. Because the second option says it cannot be extended continuously to any point outside the D. But if we have already achieved that this is continuous on D union 0, 0, right? So the third option is correct. Automatically, the second option is wrong. So what about the fourth option? F is continuous on D and can be extended continuously on to the whole of R2. That is the fourth option. So let me look at the remaining points. So 0, 0 you have already done. So what about the other points? So you look at a point on x-axis. So you have 0, 0 is we have already done. So now you take some point here, a comma 0. Okay, a is not equal to 0. So my question is whether the limit exists or not. You look at limit xy tending to a 0 x sine 1 by y. So is this exist or not? So you see x is going to a. So you can, since you can just easily observe that this x will goes to a. So but you have here sine 1 by y, right? So there is a trouble because as y going to 0, sine 1 by y will not exist. You understand that? So here x is going to a, so that is a fixed constant that is not equal to 0. X is not equal to 0. A is not equal to 0. A not equal to 0. So as x going to a, this quantity will, this function will goes to a only. But what about this sine 1 by y? What happened to that one as y tending to 0? Whether the limit exists or not? Tell me.
Does not exist.
Does not exist. So the limit xy tending to a0, x sine 1 by y does not exist. So does not exist. So what happened? If you want to extend on this point, the limit should exist there. Then only you can make it as continuously. Then only you can extend it continuously on the other points. Okay, so those points you cannot extend the function as a continuous. So only you can extend it to 0. All other points you cannot extend. So what about the fourth option? What exactly the fourth option says? F is continuous function on D and can extend continuously to the whole of R2. So what is the fourth option? Tell me whether it is correct or no, wrong.
Wrong, sir.
Wrong.
So this is wrong. So the only third option is correct. Okay. Do you understand this? Any doubt? Any doubt on this question?
No, sir.
Okay. So we will go to next question. So this is the next question. I think it is 2020 JAM question. Okay. So let us look at this. The directional derivative of a function. Okay. So you have, if the directional derivative of the function along the unit vector is 0. So what is given? The directional derivative of this function. You have this function. Z is equal to y square into e raised to 2x at 2 comma 1 2 comma minus 1 along the unit vector b is 0. That is given. Then modulus of alpha plus beta you have to find. So let us compute it directly. So since you see these functions are very nice functions, y square into e raised to 2a, so it's a differentiable function. You can directly use the definition that del f dot u, that thing you can use for the directional derivative. So let me recall. So what is the directional derivative? Du f at x naught y naught is the directional derivative that you can write as del f of x naught y naught dot u if f is differentiable. But here you can see the component functions are very nice. So here f of xy is y square into e raised to 2a. So there is no trouble to talk about the differentiability. So y square is a polynomial, e power 2x is also exponential function. So they are all differentiable. So there is no problem. So you can directly use this formula. Okay. So you first find what is del f. Del f of x naught y naught. So here x naught y naught is 'Okay. So let me write the del f. So del f of what are the things you need? One second. Yeah. Yeah. So del f of 2 comma minus 1 you have to find. Okay. So what is it? In fact, is this is a dou f by dou x at 2 comma minus 1 and dou f by dou y at 2 comma minus 1. So you compute uh, once again. Yeah. You see here, you just find a del f. So what you will get? Dou f by dou x. F is here is what is your f of xy? F of xy is in fact y square e raised to 2x, right? So you just find a dou f by dou x. Dou f by dou x is dou f. So you can find it here. Dou f by dou x. That is 2y square e raised to 2x. So dou f by dou x at a 2 comma minus 1 you have to find. So once you give 2 comma minus 1, you will get the value y is minus 1 and x is 2. So it is 2 e raised to 4 will come, right? Yeah. So here you will get 2 e raised to 4. And what about this dou f by dou y? So if you take derivative with respect to y, so dou f by dou y is so 2y e raised to 2x will come. So once you give the value 2 comma minus 1, again you will get a minus 2 e raised to 4. So that you will give minus 2 e raised to 4. Okay. So now your unit vector is given, that is alpha I plus beta j. So you can just find this directional derivative. So that is du of f at x naught y naught is in fact 2 e raised to 4 comma minus 2 e raised to 4 dot alpha beta, right? So this is there. So it is given that it is 0, right? You see the question. So this directional derivative is given as 0. So the only thing I need to find modulus of alpha plus beta. Okay. So let me look at this. This one you compute it. So what you will get? 2 alpha minus 2 beta into e raised to 4 is equal to 0. So e raised to 4 never be 0. So you will get. So this implies alpha is equal to beta, right? So you have alpha is equal to beta, but alpha and beta are unity vector. So what you know is alpha square plus beta square is 1 because it is a unity vector, right? So since alpha is equal to beta, what you can say? Alpha square plus alpha square is equal to 1. So alpha is equal to, plus or minus 1 by root 2, right? 2 alpha square is 1. So alpha square is 1 by root 2, 1 by 2, and alpha is plus or minus 1 by root 2. So if alpha is equal to 1 by root 2, then automatically beta is again 1 by root 2. So, or if alpha is equal to minus 1 by root 2, then again beta is also minus 1 by root 2. So you can just look at this modulus of alpha plus beta. So what you will get modulus of alpha plus beta? Modulus of alpha plus beta is in fact 1 by root 2 plus 1 by root 2. So it is root 2 by root 2 you will get. So that is in fact root 2, right? Modulus of root 2, that is root 2. You understand this? Do you understand this? Modulus of alpha plus modulus of beta is equal to root 2.
Yes.
It's clear. So nothing is there. You just apply the definition of directional derivative and find it. So it is given that it is 0. So you will get dou f by dou x at a 2 comma minus 1 and dou f by dou y at a 2 comma minus 1 you can find. Just substitute the value. Then you can take this directional derivative as 2 e power alpha comma minus 2 e power alpha. Sorry, 2 e power 4 comma minus 2 e power 4 dot alpha dot b you will get. Then you compare the equation, you will get alpha is equal to beta. But it is given that there is a unity vector. U is a unity vector. So alpha square plus beta square has to be 1, right? So you substitute everything there, you can find alpha. So similarly, you will get a beta there. So alpha plus beta is 2 by root 2 you will get. So 2 by root 2 is root 2. So your answer is root 2. So here is the answer, right? Root 2 is your answer. So root 2 is the answer. I'm having some trouble with this pen. Okay. Yeah. Okay. So let's just look at this another problem. Just come to another problem. I think this is, yeah, this one. Okay. You see here, this is the next question. So this is also 2020 JAM question. So you look at the problem. So you have x square sine 1 by x plus y square sine 1 by for xy not equal to 0. And x equal to 0, x not equal to 0, y equal to 0, it is x square sine 1 by x. And y not equal to 0, x equal to 0, you will get y square sine 1 by y. And x equal to y equal to 0, you have 0. So you have to look at the following things at x 0, 0, right? So for the first option is whether f is continuous at 0, 0. So what can you say about this? Whether this function is continuous at 0, 0?
By sequential argument, we can say.
Yeah. Using the sequential argument, you can say that it is continuous at 0, 0, right? So, 1 second. Yeah. Just pen has some trouble. Okay. So you have using this sequential argument, you can say this is continuous at 0, 0, right? Just look at this thing. You see, suppose you take the domain. So what is actually your domain here? So xy not equal to 0 means, first you look at this, x not equal to 0, y is equal to 0. So that is your y is equal to 0 means x-axis, right? So this component. So this is the x-axis you have, fine. And the other one is y not equal to 0 and x equal to 0. So that is your y-axis. And this 0, 0 is you should look at in a different way. 0, 0 is exactly given, its function is 0 there. And the outside points are the remaining portion of the domain. Now you see what happened to this function. You look at the function along this x-axis. So there your function is x square sine 1 by x. So once xy going to 0 along x-axis, what happens? So this x square sine 1 by x will goes to where? Where suppose x and y are going to 0. So xy is going to 0, 0. So what can you say about this function? X square sine 1 by x. This again going to 0 by modulus thing, right? So because you can bound the sine 1 by x by 1 and minus 1. So x square will goes to 0. So both n will goes to 0. So this function will goes to 0. Similarly, you can say this y square also, y square sine 1 by y also will goes to 0. Because you just bound this function. Sine 1 by y is bounded by 1. So y square into sine 1 by y will come, or y square will goes to 0. So both component will goes to 0. Now what about the first one? So whenever x and y going to 0, 0, you see that the first component is going to 0 and second component is also going to 0. The total sum has to goes to 0, right? So this also will goes to 0. So as xy going to 0, 0, all the three will goes to 0. So that is exactly equal to f of 0, 0. So f limit xy tending to 0, 0, f of xy is exactly equal to f of 0, 0. Okay, so the function is continuous at 0, 0 is the correct option. So the first option is wrong. F is not continuous at 0, 0 is wrong. Now you look at the second option. What is the second one? Dou f by dou x is continuous and dou f by dou y is not continuous. So let me first compute what is this dou f by dou x and dou f by dou y. Okay, just find dou f by dou x and dou f by dou y. Okay, so just find dou f by dou x at a 0, 0 and dou f by dou y at a 0, 0. So let us look at this. So what is your dou f by dou x? That is fx at a 0, 0 I have defined. So that is limit h tending to 0, f of 0 plus h 0 minus f of 0, 0 divided by h. That is your limit h tends to 0, f of fx at a 0, 0 is this one. So you just compute these values. So this is equal to limit h tending to 0, f of h0 minus f of 0, 0 divided by h. What is f of 0, 0? You look at here, f of 0, 0 is 0, right? And fh0 is what? h0 means y component is 0. Y component is 0, it means the second function you have to take, x square sine 1 by x. That is a function, right? So you just club everything. So what you will get? So this will be equal to limit h tending to 0. So here second component is 0. So it's a function alone in x. So that will be h square sine 1 by h and divided by h will be there. So this h will cancel. So the remaining is limit h tending to 0 h sine 1 by h. So this quantity is 0, right? Because sine 1 by h you can bound by 1 and minus 1. Again, left hand and right hand will goes to 0. So entirely you will get 0. So fx at a 0, 0 you will get 0. So what about fy at a 0, 0? You can do in the similar way, right? Fy at a 0, 0, you have to take this third function. Third one, y square into sine 1 by y. Because you will get x is 0 there and y component you will get h. The same way you can compute. So similarly you can do it. So you will get fy at 0, 0 is also 0. Fy at 0, 0 also you will get 0. Similar way, no changes, only the component is changing. Here you have 0 plus h. Instead of that, you will get here 0 plus h. The second component will be 0 plus h. First component will be 0. That is the only difference. Okay. So you can just compute it. You will get it is nothing but fy at 0, 0 is also 0. Now, what about the second option? So what you have to look at is whether this dou f by dou x is continuous at 0, 0. Okay. So in order to check whether it is continuous at 0, 0, what you have to look at? You should look at the small neighborhood of 0, 0, right? So you should check whether in the small neighborhood the dou f by dou x are existing and or if it is going to 0. Okay. So first of all, you can directly compute a partial derivative apart from this 0, 0. So you should find dou f by dou x. What is dou f by dou x? Tell me. So f. So you can just look at the function. So in the x-axis your function is x square sine 1 by x. Okay, x-axis is y is equal to 0. That is the x-axis. There your function is x square sine 1 by x. Now you find dou f by dou x on x-axis. So what you will get dou f by dou x there? Tell me. Directly you can find. So on x-axis f of xy is x square sine 1 by x. So what is your dou f by dou x there? So you just take the derivative of this one, x square into cos 1 by x. So only trouble is there for x equal to 0. So I am not looking for the case x is equal to 0. So x not equal to 0 I am talking. With x not equal to 0. Okay. And so at x equal to 0, you cannot have this function. There you have to look at it in a different way. You have to use the definition of the partial derivatives. Otherwise, you can directly compute the partial derivatives. So what you will get x square into cos 1 by x into what is the derivative of 1 by x? That is minus 1 by x square plus sine 1 by x. What is the derivative? That is cos 1 by. Yeah, that we have done. Then you have to apply the product rule, right? So 2x into sine 1 by x. Yeah. So you just compute it. So this x square will cancel. So the remaining is minus cos 1 by x plus 2x sine 1 by x. So this is the partial derivative of f at on the x-axis, right? So now you look at these derivatives, what you can say about this one? Whether this is continuous at 0. So whether the partial derivative is continuous at 0. As x going to 0, what happened to this second component? As x going to 0, what happened to the second component? 2x into sine 1 by x.
It goes to 0.
It goes to
Yeah,
0.
it will goes to 0. What about the first component?
The limit shall not exist.
Does not
Yeah,
exist.
limit does not exist. Okay, does not exist. So the limit does not exist as x tends to 0. So this function is not continuous at a 0, 0, right? So as x, not even the limit exists. So what we can say is this dou f by dou x is not continuous at a 0, but dou f by dou x at a 0, 0 is existing, but it is not continuous. So what about the second option then? Second option, what it is saying, dou f by dou x is continuous, but dou f by dou y is not continuous. But we got that dou f by dou x is not continuous. Okay. So from that itself, you can conclude that second option is wrong. You understand this? Is that clear?
Yes, sir.
Yeah. So you can say this this one is wrong. So what about the third option? Let it be there. Now you look at the fourth option. So similar way. So the similar way what we computed this way, the similar way you can compute this dou f by dou y is also not continuous. Okay, you can just find the dou f by dou y. Everything will be in y. That's all. That is the only difference. So I computed dou f by dou x. Everything will be in x. So once you compute dou f by dou y, you have to consider this function y square into sine 1 by y. Again, you can take the derivative. So 2y into cos 2y into sine 1 by y plus cos 1 by y minus cos 1 by y will come. But there also the limit does not exist at 0, 0. So you can see that the dou f by dou y is also not continuous at 0, 0. Okay. So dou f by dou y is also not continuous at 0, 0. Dou f by dou x is also not continuous at 0, 0. But both are existing. That is the first thing. Now you just look at the whether the f is differentiable at 0, 0 or not. So how do you check? To check differentiability, I already told the derivative is given in terms of gradient. So only thing you need to verify. One second. So the only thing you need to verify these things. You have del f at x naught y naught, that is dou f by dou x at x naught y naught, and dou f by dou y at x naught y naught. So this is your del f. Now if you look at if you want to check whether the function is differentiable, so what you have to do, your df at x naught y naught is del f dot this del f only. So what are the things you have to verify is limit. This is in fact your del f, that is your derivative. Once the derivative exists, it should be del f. So the remaining things you need to verify this thing, limit h1 comma h2 tends to 0, 0. So what happened to this one? F of x naught plus h1 y naught plus h2 minus f of x naught y naught minus del f of x naught y naught dot h1 h2. This is modulus is here, divided by norm of h, that is root of h1 square plus h2 square. So if this quantity is equal to 0, we can say f is differentiable and the derivative is del f. So the only thing I wanted to tell you that once it is differentiable, its derivative has to be del f. So you only need to verify whether this quantity is 0 or not. If it is 0, this is differentiable and the derivative is del f. If it is not 0, then it is not differentiable. That's all. So you have already obtained this del f. We need to check everything at 0, 0. So dou f by dou x at 0, 0 is 0, that we have computed. Similarly, dou f by dou y also at 0, 0 also we computed. So what is del f at 0, 0? So we have del f at 0, 0, that is in fact 0. And what about the f of 0, 0? That is also 0, right? F of 0, 0 is also 0. So you club everything here. So you only need to look at the 0, 0. This implies, so you look at the limit. So consider limit h1 comma h2 tending to 0, 0 modulus. So f of 0 plus h1 is h1 comma h2 minus f of 0, 0, that is 0, and del f at 0, 0, that is also 0. So only thing you will look at this one, f of h1 comma h2, right? Modulus. So modulus value. So I just divided by root of h1 square plus h2 square. This is the quantity you have to look at. So so you need to check whether this is equal to 0 or not. Okay. So you just substitute the values here. The limit h1 comma h2 tends to 0, 0. So what is your f of h1 h2? F is given by this equation, right? X square sine 1 by x plus y square sine 1 by y, right? So you just give those values. So what you will get? So each cases you can do. So each cases you can separately do, or you can directly substitute that. This value will give you h square, h1 square sine 1 by h1 plus modulus h2 square sine 1 by h2 divided by root h1 square plus h2 square. So this will be, you can say this is less than or equal to, I just use the triangle inequality of modulus, and sine is bounded by 1. So this will be limit h1 h2 tends to 0, 0. So what you will get? H1 square plus h2 square divided by root h1 square plus h2 square. So this quantity will goes to 0, right? Because numerator you have the highest power. So when you if you want to look at in a different way, you can just convert it into polar coordinate. Then here you will get a denominator, you will get r square, numerator you will get r square cos square theta. So this quantity will goes to 0. So you will get the function is differentiable. So the conclusion is f is differentiable. F is differentiable, that is God, and we have already seen that this dou f by dou x and dou f by dou x are not continuous. So the fourth option is correct. Okay. The fourth option is correct.
Sir, we are
Yeah.
checking for xy not equal 0 only, no sir. For other case,
Other case
also
also automatically will come because it is x square sine 1 by x, right? The same function we are looking there. So if you want to look at each one, you can do. No problem.
okay.
The same way you can do.
But
Same
we
way
have
you
to check for all function, no sir. For
Yeah,
different
all function you have to check. That is correct. You have to check for all function. But here every function is are same. So when you look at the second part, what you have to do? Your x component is not 0 and y is 0, right? So only there h2 part is when you give the h2 will be 0. You can take always. So h1 is non-zero. So there then your equation reduces to the form. So let me check it. So here what you have, yeah, the final stage, you don't have a h2 won't be there. H2 will be 0, right? Along the y x-axis, if you are looking, h2 will be 0. So the expression will be h1 square divided by root h1 square will come. So that also will go to 0.
Okay, sir.
Similarly, for the third part, h1 will be 0 and h2 will be there. You understand that?
Yes, sir.
Yeah. So each case you have to check That is correct, but that follows immediately. That is why I have not included that thing in separate way. So the answer is fourth one. F is differentiable, and both dou f by dou x and dou f by dou y are not continuous. So this is the correct answer. So do you understand this?
Yes,
Do
sir.
you understand this? Okay. So let us go to one more problem. Yeah. So you guys can easily try this one. So the first thing is f is continuous. So how do you check it, whether f is continuous or not?
Whether the limit of the function going to
Where it goes, limit is
0.
equal to
0.
0. Why?
So you have to check, sir.
Yeah, because this quantity you see, mod x by mod x plus mod y, you can always say this is less than or equal to 1. Correct? Because mod x is less than or equal to mod x plus mod y. So you are adding a positive term with the mod x, that is mod y. So this denominator is bigger. So this is always less than or equal to 1. Now you see what happened to this modulus of f of x1. This is less than or equal to root of x raised to 4 plus y square. Because this quantity is less than 1. So the remaining is root of x raised to 4 plus y square. So once you send xy tending to 0, 0, what happened to this left side? This will goes to 0. X and y are going to 0. So x raised to 4 plus y square will goes to 0. So the root of those value will goes to 0. So this side will goes to 0, but the left side this is always positive thing. So the in between thing also has to goes to 0. So what you will get? Limit xy tending to 0, 0, f of xy is 0. You understand this?
Yes, sir.
Yeah. What about the second one? Just verify fx at 0, 0. Just try yourself. Fx at 0, 0, whether it exists or not. So how do you check it?
I think it does.
What is the value you got? Fx at dou f by dou x at 0, 0?
I got 0.
0. Yes, it's correct. You just see here. You look at this fx at 0, 0. So this is by definition, it is limit h tends to 0. F of 0 plus h is 0 plus h comma 0 f of 0, 0 divided by h. Okay. So 0 plus h, you are making only increment on x component. Now you combine everything. So what is f of 0, 0? That is 0. So you can just look at this 0 plus h. You just that is f of h. This is limit h tending to 0. F of h0 minus f of 0, 0 divided by h, right? So you just look at what is f of h0. You substitute there. So y component is 0. Only s component is there. That is limit h tending to 0. Mod h divided by mod h will be there, because y component is 0, so mod y is not there. So plus into root of h raised to 4 plus y component is 0. So this is remaining. So divided by h is there. This mod h by mod h will be 1. So square root of h raised to 4 will give you h square, right? So this quantity is this is equal to limit h tending to 0, h square by h you will get. So h will, one h will cancel. So this is limit h tends to 0, h, that is equal to 0. You understand this?
Yes,
Is it clear?
sir.
Yes. So fx at 0, 0 is 0. So what about fy at 0, 0? Can you find it? Fy at 0, 0? Similar way you can find fy at 0, 0. So that is limit h tends to 0, f of 0 comma 0 plus h is that is h minus f of 0, 0 divided by h. Only the increment in y component. So you see here 0 comma h you have to substitute. What is your function? Mod x divided by mod x plus mod y, right? So once you give x is equal to 0, numerator becomes 0. So numerator becomes 0, so the entire thing becomes 0, right? So denominator you have mod h. So what you will get? This is in fact limit h tends to 0. This is in fact 0, right? 0 divided by 0 plus h something 0 plus h square you will get. So but in this quantity is entirely 0. And 0 is there divided by h. So this numerator is always 0. So you will get 0. So fy at 0, 0 is also 0. So both exist. You understand? Fx at 0, 0 is 0 and fy at 0, 0 is 0. Both exist. So what about what are the options? What are the correct options?
First and last.
Yeah, f is continuous and this one is dou f by dou x at 0, 0 and dou f by dou y at 0, 0. So both are 0. So these two are wrong. You understand that? Clear? Clear?
Yes, sir.
Okay. Now, so if you want, I have give you more problems. So I have one more problem. So you can just try this one. So you just find the directional derivative in the direction. So here you have to use the definition. Okay. So just I may just give you these problems. Then it is different. You cannot directly compute it. Okay. You have to use the definition because we don't know whether the function is differentiable or not. So it's better to compute in a direct way. So what was the definition? du of f at x naught y naught is equal to limit t tending to 0 f of x naught plus tu1 y naught plus tu2 minus f of x naught y naught divided by t, right? This was our definition for directional derivative. U is a unity vector. You just check whether the given vector is unity vector. So first you have to check whether the given vector is unity vector. If it is not a unity vector, you divide it by its length, then it becomes a unity vector. Okay. So what is the things? The given one is unity vector, right? Because 4 by 5 whole square plus 3 by 5 whole square. So it will be 16 plus 9, it is 25. 25 by 25, so it will be 1, right? So 4 square plus 3 square is 5 square. Yeah. So you will get is 1. So it's a given one is a unity vector, so there is no problem. So some cases they will not give unity vector. So what you have to do to make it as a unity vector, you just divide by its length, then it becomes a unity vector. Now you look at 0, 0, we need to find the directional derivative. So everything you substitute here. So limit t tending to 0, f of x naught y naught is x naught is 0 and y naught is 0. So it is 0 comma 0 plus u1 is 4 by 5. So t 4 by 5 and y0 is 0. So 0 plus t 3 by 5. F of 0, 0 is 0. So divided by t is there. So now everything you can substitute in the given equation. So what you will get? So limit t tending to 0. F of 4 by 5t 3 by 5t divided by t, right? So you can just substitute all the values. So this will be equal to, so what is the thing you have? X cube plus y cube divided by x square minus y square, right? So you just substitute here. So limit t tending to 0, x cube plus y cube. So 4 by 5 t whole cube plus 3 by 5 t whole cube divided by x square minus y square. So 4 by 5 t whole square minus 3 by 5 t square. And one more t is there in the denominator, that I will write it here. So t cube, everything will cancel. So numerator you have t cube, that you can take common. And here also you have t square, you can take it as common. Then one t is there. So t cube will cancel. The remaining is 4 by 5 cube plus 3 by 5 cube divided by 4 by 5 square minus 3 by 5 square. You just compute this value. Okay, this is the final answer. Just compute it. So this will give the final answer. You understand this? Is that clear?
Yes, sir.
Okay. So just to use the definition, then you can. So I will give you. So one more question I wanted to give you. Yeah, this is the latest question. This is for last CSIR question. Okay. Last year CSIR question. Just few months back this happens, right? CSIR UGC exam. These questions. You just look at this. So is it visible? Is it visible? Fine. If the question is visible, or if you want to make it is larger, I can.
No, sir, it's visible.
Yes, visible. Fine. Okay. So now see, the problem is here you have f of xy is equal to x minus y whole square into sine 1 by x minus y, where x not equal to y, and 0 for x equal to y. The first option is f is continuous at a 0, 0. So what is your answer? Tell me whether f is continuous or not. So what is the function you have? F of xy is x minus y square into sine of 1 by x minus y. So you wanted to check whether the continuity, whether the function is continuous at a 0, 0. What do you have to do? So you have to do limit xy tending to 0, 0, f of xy you have to compute. So here you see, here you have 1 by x minus y and x minus y square. So it is better to substitute, put some z is equal to x minus y. Okay, then you can convert it as a single variable problem. So once you substitute x is equal to x minus y is equal to z, as your xy going to 0, 0, your z also will goes to 0. So this is same as to say limit z tending to 0, z square sine 1 by z. Both has the same behavior. Okay. So what happened to this function z square sine 1 by z? What should be its value? Tell me.
0.
0. So it should be 0. So the limit xy tends to 0, 0, f of xy is 0. So this is some trick. You can just convert, if it is possible, not all the problems. For this problem, you can convert this x minus y as z. Substitute this x minus y is equal to z. So z square into sine 1 by z will come. So the limit will be 0. So you got it. F is continuous at a 0, 0. That is a right answer, right? The first option is correct. F is continuous at a 0, 0. So what about the partial derivative? Just check it. The second option is the partial derivative fx does not exist at 0, 0. Okay. So let me look at the partial derivatives. So you just compute. So I can do it here. So what is fx at 0, 0? That is limit h tending to 0, f of h0 minus f of 0, 0 divided by h. Okay. What should be that? You just look at what is f of h0. Your y is 0. So throughout you give h. So this will be limit h tends to 0, h square sine 1 by h divided by h. So h will cancel. So this is in fact 0, right? Because h will cancel, then h into sine 1 by h will come. So h sine 1 by h is going to 0 because the sine 1 by h is bounded by 1. So this value is 0. Clear? So fx at 0, 0 is 0. So the partial derivative fx does not exist at 0, 0 is a wrong option, right? The second option is wrong. What about the third option? Can you tell me what about the third option? What about the partial derivative with respect to x? You find the fx first, partial derivative for the other points not equal to 0. So if you want to check the continuity, you should look at the partial derivative near 0, 0, right? So you should find the partial derivative in the neighborhood of 0, 0. So you look at the partial derivative first. So what is the partial derivative of f? So you find dou f by dou x. So you find fx or find dou f by dou x. Okay, fx at xy, general points you find. So what will be the partial derivatives? Your function is x minus y whole square into sine 1 by xy. So you have to apply the product rule. Y you can treat as constant. So first you have x minus y whole square, then the derivative of sine, that is cos of 1 by x minus y, and you have to use the quotient, the function of function rule. So 1 by x minus y is there, their derivative is minus 1 by x minus y whole square. Plus, so you are treating y as constant, only take the derivative with respect to x. So you will get 2 into x minus y into sine 1 by x minus y. So this is the final thing you will get. But here you have x minus y square, here also x minus y square, that will cancel. So the remaining is minus cos 1 by x minus y plus 2 into x minus y into sine 1 by x minus y. Now tell me whether the limit exists or not. Xy tending to 0, 0, whether the limit exists or not. As xy tending to 0,
No,
0,
sir.
what happened to the second term?
0
Yeah, it will goes to 0. What about the first term?
does not exist.
Does not exist. So the limit does not exist. So what you can conclude? The second option. What about the third option? The partial derivative fx is continuous at 0, 0 is wrong, right? The partial derivative fx at continuous is wrong. So what about the last option? Now you wanted to check whether the function is differentiable at 0, 0. Okay. So before finding the derivative, before checking whether it is differentiable, you need to find a del f. So to find del f, you need fy at 0, 0. So you find fy at 0, 0 first. What is fy at 0, 0? Fy at 0, 0 is limit h tends to 0, f of 0 comma h minus f of 0, 0 divided by h. Okay. So what is f of 0 comma h? Just look at here. Yeah, everywhere, wherever x, you give h there. So you will get the same way you can find it. So you will get the limit h tends to 0, h square sine minus h, right? Minus h divided by h will come. So that is minus of sin h. That doesn't matter. So this is limit h tends to 0 minus h square sine 1 by h by h. Again, you can, this h will cancel, minus h will come. But anyway, you can sine 1 by h, you can bound by 1 and minus 1. So again, this will give you 0. Or you can take minus outside, the remaining portion is 0. So you will get 0 only. So fy at 0, 0 is also 0. So what should be the expected derivative? If it exists, the derivative should be, so you so if f is differentiable, then derivative df at 0, 0 should be equal to del f at 0, 0, right? So that is in fact 0 vector. So now you only need to check whether that corresponding limit is going to 0. So consider limit h1 comma h2 going to 0, 0 with the f of h1 h2 minus f of 0, 0 minus del f of 0, 0 dot h1 h2 modulus divided by root of h1 square plus h2. We need to show this is, if it is 0, you are achieved, the function is differentiable, then you can conclude. The only thing you need to check whether this is 0 or not. Okay, so you can just compute this value. So all the things you substitute, f of 0, 0 is 0, this del f component is 0. The only thing you need to check whether limit h1 h2 going to 0, 0 modulus f of h1 h2 divided by root h1 square plus h2 square. You check whether this is 0 or not. So you substitute f of h1 h2. What are the values you can have? Here you have h1 minus h2 square divided by sine h1 minus h2 will come. You can just substitute the values. So here you will get limit h1 comma h2 tends to 0, 0. You substitute the value h1 minus h2 square into sine of 1 by its modulus is there, h1 minus h2 is there, divided by root of h1 square plus h2 square. Now you can bound this by, this is less than or equal to limit h tends to h1 comma h2. Okay, h1 comma h2 tends to 0, 0 modulus h1 minus h2 whole square, or this is modulus is not needed in fact because it is a square. This sign is bounded by 1 divided by root of h1 square plus h2 square. You can easily verify this is going to 0, right? Because you have a higher powers on the numerator. So this should be 0. If you want to check it precisely, you substitute h1 equal to r cos theta and h2 equal to r sin theta. The denominator you will get r, and numerator you will get r square into cos square theta minus sin square theta. So the r will cancel, the one r is remaining. So once h1 h2 going to 0, 0, r will goes to 0. So if you want, I can write it here. So this is the thing. So you will get a limit r tending to 0. H1 minus h2 square means r square into cos square theta minus sin square theta divided by, here you have r. So this r will be. So whatever the angle you take, as r tending to 0, you will get 0. Okay. So this will be 0 always. So what exactly you are getting is this left hand side is 0. So right hand side is 0. So this quantity has to be 0. So because this is always greater than or equal to 0, so this quantity has to be 0. That means f is differentiable and the derivative is del f at 0, 0. That is 0, 0. So that is your derivative. So what is the conclusion? The conclusion is f is differentiable and f is differentiable at 0, 0. That is the correct answer. So what are the options? What are the correct options? First option is correct. F is continuous at 0, 0. And this partial derivative does not exist is wrong. Second option is wrong. Third option is wrong. And fourth option is correct. First and fourth option is correct. So this first option and fourth option is correct. You understand this? Is that clear?
Sir, in fourth definition, f is differentiable. There, I have some doubts, sir.
Why?
That formula del f of 0, 0 dot product, sir. That is product of h1, h2.
Yeah, dot product you are taking.
Okay, sir. Okay, sir.
Yeah, that is dot product. Dot product h1, h2. Del f
Okay, sir.
it is 0, 0 dot h1, h2. So
Okay,
once a function of two variable is differentiable, its derivative is del f. Then so that this quantity should goes to 0. So such a functions are called differentiable functions. So if this quantity is 0, you can say f is differentiable and the derivative should be equal to this one vector. This vector is the derivative. That is the definition.
Okay, sir.
I'm Gayatri.
Yeah.
I have done my graduation from Randa House College, Delhi. The class was very nice, sir. Your explanations were clear and was easy to understand. And you have discussed some of the previous year questions that was really useful. Thank you, sir. Thank you.
I'm Deepak from Tamil Nadu.
Yeah,
Sir,
Deepak.
your session was so valuable, sir. I learned more from your class, sir. Thank you, sir.
Deepak, could you introduce where are you studying currently?
Sir, I'm completed M.Sc in St. Xavier's College, sir. And I'm preparing for NET exam, sir.
Okay. Thank you, Deepak.
Thank you, sir.
Good afternoon,
Gauri?
sir. I am Gauri from St. Xavier's College. The class was really informative and refreshing, sir. Moreover, when you discussed the previous year questions of JAM exam, the theory part you took was much more clear when you discussed the questions. Thank you for spending your valuable time and knowledge with us, sir. Thank you so much.
Gauri?
Hi, sir.
Yes.
My name is Hari. I'm currently third year BSc Maths student from TMG College, Calicut. First of all, thank you, sir, for such a wonderful class, and it's really helpful us. And you explained every questions and theory part very clearly. And thank you, sir.
I'm a second year student, and the theory work was very nice. And you have discussed a handful of questions, which I think is very useful for our JAM preparation. Thank you, sir, and thank you, Vinod, sir, for organizing this class. Thank you.
Hi, sir. I'm Zahra from TMG College, Tirur. And your class is very nice, very clear and interesting. And thank you, Vinod sir, for conducting this section. Thank you once again, sir.
Verma from Zamurian's Guriarpan College, Calicut. And this section was wonderful, and I learned a lot from this section. And thanks for conducting an informative section for us. Thank you so much.
Hello, sir. I am Dharmendra from Visakhapatnam, and my native is UP Agra. I am doing job here in library in BARC Visakhapatnam. I learned more things in this class, and I enjoyed also, and I enjoyed previous year question also. Can sir tell about his PhD journey, about differential geometry,
PhD experiences?
Yeah, I heard that. I completed PhD in broadly in Riemannian geometry, and my area is somewhat connected with the probability measures and geometry. So it's a new branch of mathematics, or you can say it's information geometry. is deal with statistical manifolds and etc. So I joined there in IIST using this CSIR exam. I cleared CSIR exam, and after attending the interview, I joined the. I took around 6 years to complete the PhD, and I go. So since the things I to get the publications, it took almost 6 years to get a publication. So that is somewhat difficulty is there. So while doing those kind of area, you may feel some difficult, but you have to continuously work, and then you will get some work. That is the that
Yeah,
will
that is
naturally
the-
happen, right? Yeah, that will naturally
Yeah,
happen.
that is always the case. If you are working in a hardcore area, then certainly you need more time.
Yeah. So
Yes.
it was nice, and if you are interested in geometry, you can learn some basic books like Introduction to Manifolds by Loring 2. That is a very introductory good book. So you can start learning from there, and after that you can learn Smooth Manifolds by John M. Lee. They are the very good books. So then you will be able to learn any of its parts. You can look at. There are a lot of good books available in that area. So for the basic part, you can take these two and Lee. They are the best books, I feel.
What are
Mahesh.
prerequisites for this topic?
Pardon?
What are prerequisites for Riemann geometry?
Yeah, a little bit of multivariable calculus. That is the first thing, and then little bit of topology is also needed. So topology is in fact a topological part. Topology is there, and this multivariable calculus you need. So some linear algebra also needed.
Okay, Mahesh, it will be very good if you can include some references as a part of your slides that may be shared as a PDF along with the recordings of our today's session.
Yeah, I included some references for these multivariable things. 2 references I have included.
Yeah, you may include some introductory references to Riemannian geometry as well. So some PhD aspirants maybe find it useful.
Okay.
Okay, thank you, Dharmendra. Others?
Hello,
Yes,
sir. Good afternoon, sir. I am Shikha from Birla Institute of Technology, Mesra, Jharkhand, second year M.Sc student. So your session was really very nice and informative. Thank you, sir, for taking out time for us, and thank you, Vinod sir, for organizing such sessions. Thank you, sir.
Thank you, Shikha. Gopika? Yes, Gopika.
Hello, sir.
Yes.
Hello, sir. I'm Gopika from Zamorin's JRF College, Kozhikode. Today's session is really nice. Thank you so much, sir, taking such a wonderful class. It's really helpful for preparing our jam. Thank you so much, sir. The theory part and the questions you discussed is really nice. And thank you, Vinod, sir, for conducting this nice session.
Okay, thank you, Gopika. Okay, any others?
Sir, am I audible?
Yeah. Yes.
Sir, I am Anamika, and I'm also from Zamorin's JRF College, Kozhikode. Thank you, sir, for the session. It was wonderful, and the presentation you prepared and the questions you collected was really nice. And thank you, sir, for this wonderful session and your valuable time. Thank you, Vinod, sir.
Thank you, Anamika. Okay, any others?
Good afternoon, sir. Usually I had a fear of those questions because that was my year 2021 and I really messed that section up. After this it got cleared. I didn't even go back to check whether they were what should be the correct answer, etc. Thank you. Like I'm not scared of them at least.
So Mahesh, Vinod is our topper in our CSIR NET examination. She has scored all India rank 22 from our group. She is currently doing M.Sc at Iritty.
Yeah. Okay. Congrats. Yeah.
Thank you, Vina, and all the very best. Again, congrats for your achievement.
Thank you, sir.
Any others?
Hi, sir.
Yeah.
Sir, I am Lakshmi from Ernakulam Central College. Thank you so much, Mahesh sir, for this wonderful session. It was very helpful for us. And thank you, Vinod sir, for conducting the session.
So I am Amal. I am from Iritty Mahatma Gandhi College. The session was really nice and the topics clear. The content that you had taken in the theory part was very helpful and the questions were also really helpful. Thank you, sir, for such a session. Thank you.
Thank you, Amal. Once again, thanks for being with us. Thanks for the session. Let us wind up here. Thank you again. Thank you, everyone, and wish you all the best.